Hey class, today we're going to start chapter 14. It is the last physics unit. Then we're going to do a week-long project, and then we're going to learn about astronomy. This section is going to talk about work and machines. And some of it should sound familiar because you did hit on some simple machines when you were in junior high, such as a lever and pulley. And we're going to go in a little bit more detail about that. So our first section, we're going to cover work and power. We're going to first define work and then power. So our first question is, what is work? In science, we define work as the product of force and distance. So if you think back to your math class, anytime you hear the word product, we should be multiplying force times distance is actually going to equal work. So keeping that formula in mind, we have to realize in order for us to do work, we need to have force, and it has to move some type of distance. So this brings up in the idea, when you have force, how do I know if the force that you're applying is actually doing and converting into work? For force to do work on any kind of object, that force should act in the same direction that the object moves. So for example, if you exert an upward force, in order for that to do work, the object should also be moving upwards. Just a tidbit fact, if there is no movement, no work has been done. If you think back to the equation I just put on the last slide, if there's no movement, it didn't move any distance. And since distance is part of the formula, and it would be 0, anything times 0 is 0. So what about the force that does not act in the direction an object moves? Well, it just equates that force doesn't do any work on that object. So work requires motion, first key thing, and work depends on the direction of the force. Here, I'm going to talk about 3 statements and apply it to something that is done every day if you ever go on vacation. Our first statement says, if all of the force acts in the same direction as motion, all of the force is going to do work. So a good example of this is if you are pulling a suitcase, but instead of pulling it a normal way, you pull it horizontally along the ground. Notice you are pulling to the right in this picture, and the motion of the object is going to the right. This means that all of the force that you are applying is doing work. Looking at statement number 2. If part of the force is in the direction of motion, then only that part is going to do work. Let's look at a real-life example. Say you were pulling a suitcase the normal way. Not only do you have to pull up on the handle in order to get that diagonal of the suitcase, but you also have to pull to the right or forward to get it moving. However, the direction of the object is still moving to the right. Only these 2 arrows are doing work. This arrow pointing up when you lift your suitcase handle up does no work because it's not in the direction that suitcase is moving. And the last statement says if none of the force is in the direction of motion, then that force does absolutely no work. A good example of this is if you are carrying something or lifting something. For example, if you are lifting an object up and you're carrying it forward, the force is not in the same direction as motion. So technically, according to science, when you are holding something and walking across the room, you are not doing any work on that object. Another example that we could look at is a weightlifter lifting a barbell. Work is actually done when a force acts on the barbell in the direction that it moves. So for example, if the weightlifter pulls up and the barbell moves up, work is being done. However, there are times when a weightlifter is not doing any work. A good example of this is if a weightlifter is holding a barbell above his head. Yes, he is still applying a force in order to keep it above his head, but if he's just holding it up there and it's not moving, he's technically not doing any work. Because like we said, if it's not moving, or what we call stationary or at rest, then no work is being done because my distance is 0. So looking back at this equation that I brought up at the very beginning, work equals force times distance. We're going to be using this equation, and we also have to realize what units go with these calculations. So when we look at units, we learned what force was in chapter 13 and 14. Force is usually a push or pull on an object, and we relate it into newtons, so that is a capital N. Distance, we learned in chapter 12. Distance is measured in meters for our SI unit, which is a lowercase m. So since we're multiplying these two values, work is technically 1 Newton times meter, or 1 Newton meter. But we don't write that, and we just shorthand it. And our shorthand version of a Newton meter is called a joule, which is a capital J. And this is what we classify as the SI unit of work. This is not the only unit that's used in science. Work can also be used in calories, but SI unit is joule. Now let's use that formula. It says a weightlifter raises a 1600 Newton barbell to a height of 2 meters. Calculate the work done to raise the barbell. Okay, we got to recall our equation. Work equals force times distance. It says calculate the work, which means that's what we're trying to find. That is my unknown. That means I need to have a number for force and distance. If we look at this 1600 Newton barbell, we should recognize Newton is a unit for force, so 1600 should go in for force. Then here it says a height of 2 meters. Meters should give away that this is a distance. So 1600 times 2, we should get 3200. However, I will always mark off if you do not have labels, because labels are very important in science. So we have to make sure if we're looking for work, you need to put the unit joules with your answer. So what is power then if we know that work is distance times force? Well, power is essentially just the rate of doing work. Whenever you hear rate, usually this is talking about like a time frame. So essentially, how much work are you doing in a set amount of time? Or how much work are you doing, how much time does it take you to do a set amount of work, essentially. So, a couple things to note about power. You are going to be considered more powerful or exert more power if you do work at a faster rate. So there are 2 ways that you could look at this statement. The first way that you could look at this statement is to increase your power. You can increase the amount of work that you do in a given time. So that means you have a set time, you need to see who does the most work. Or you can do a given amount of work in less time. And I equated this to football boys. They have to push a sled, which is just a heavy object, to help when they tackle. If we look at this first statement, you can increase the amount of work done in a given time. So let's say 2 boys were pushing a sled at football. Whoever pushed the sled the farthest in 30 seconds has the most power because they did the most work. Or we could look at it. Let's say I wanted all the boys to push 50 yards. Whoever did that in the least amount of time is going to have more power. So we can even look at this when clearing a driveway with snow. Work is required to move snow from one location to another. And if I gave one person a shovel and one person a snowblower and said, who is going to do the most amount of work or who's going to do the work faster, most of you guys are going to be like, the snowblower is going to. And the reason for that is because the snowblower has more power. And you could look at this one of 2 ways. You could look at the snowblower has more power because it can remove the same amount of snow much faster. So if you were having a competition of clearing driveways, it's going to clear the driveway faster. Or you could look at it by saying the snowblower has more power because it can remove more snow in a set or a given amount of time. So if you had a competition, who can clear the most driveways in an hour, the one who clears the more snow is going to be more powerful. So if we look at our equation for power, power deals with work and time. And what you see here is we are going to be dividing. Power equals work divided by time. And I always like to look at these and see how everything is related. So we have power and work, and time and power. Here, if we increase my work, we should recognize that my power will also increase, as long as time stays the same. This is a direct relationship. Here, if we increase the time it takes to do work, we're going to notice that our power actually goes down, and this is an inverse relationship. So let's look about that equation and the units. We already just talked about the SI unit for work is joules. We should recognize that times unit is seconds. So what exactly is the SI unit for power? The SI unit for power is watt, and the symbol is a capital W. If you've ever heard of your parents talk about 60-watt light bulbs, they're talking about the power that light bulb holds or generates. 75-watt light bulbs, things like that. So let's actually use that equation to calculate how much power is being used to lift a box. Here it says to lift a box, you exert 72 joules of work in a time of 2 seconds. We have to realize that our power equation equals work divided by time. So it's asking for power. That is our unknown, so we're going to throw X in for that. And then so we need to have two values, work and time. Here it says 72 joules of work, so we're going to plug that in for work. And then it says my time is 2 seconds. If we look at this, 72 divided by 2, and if you are unsure what it is, make sure you guys plug it into your calculator because you will always have it. This is going to equal 36. Again, we do not like naked numbers, so we want to make sure that we put a unit on this, and power is in watts. Now here I have a problem that's a little bit more challenging because we need to recognize a couple things. It says you lift a book from the floor to a bookshelf 2 meters above the ground. How much power is used if the upward force is 15 newtons and you do the work in 3 seconds, not 30. So we should recognize that work, it's asking for power. We should recognize that it's asking for power. So power equals work divided by time. So power is our unknown. We're going to throw X in for power. And it's asking for work and time. Well, if we read this problem, we have our time. We know that it's 3 seconds, but we don't know what our work is. It doesn't give us work. It gives us distance and it gives us a force. So this is when we're going to be like, hey, we have two unknowns. So we have to actually use our work equation, which is force times distance, in order to find it. For our work equation, work is going to equal 15 newtons times a distance of 2, which actually equals 30, and this is 30 joules of work. Then we can take this 30 joules and plug it down here. So 30 divided by 3 actually gives us 10 watts of power. To finish out this lesson, we're going to look at another unit that we can actually use for power. We learned that watt was the unit that we typically use, but you might have also heard of another common unit called horsepower. If you've ever worked with engines, they usually say, oh, this is a certain amount of horsepower engine. Horsepower is equal to 746 watts. So how did this term come about? James Watt, who actually, what the term watts is named after, was actually looking for a way to compare how much power his invention of steam engines could produce. And so This happened around the 1700s because he lived between 1736 to 1819. So he had to compare it to what was the most commonly used source of power during that time. And the most common source of power were horses. Horses were the ones that drew buggies. It was the one who pulled the plow in order to farm land. It pulled carriages to get people from one location to another. So they were the powerhouse, basically, in that time period. So this is where the term horsepower comes from. Okay. Before I finish this lesson, I just want to go back to one slide and add something in that I kind of forgot to talk about. Please make sure that you guys get this in your notes. And it has to do with the relationship between force and work and distance and work. Here, please note in your notes that if force increases, so does work, and that this is a direct relationship. And if your distance increases, so does your work. This is also a direct relationship. So again, please make sure you pause, get this in your notes as well. Okay. And that is the end of today's lesson. If you have any questions, please make sure that you ask, and I hope you guys have a great day.